Okay, so this is the fifth question from today, question number 15, with some of a lovely pulley and a few bits and pieces flying about all over the place. Let's see how we get on with this one. Okay, so I've drawn a picture here, a little diagram of our ball and our stone connected by a string going over a pulley. The ball has got a mass of 0.6 kilos, so that tells us that the force of gravity is 0.6 g, and for the stone, mass 1.4 kilos, so 1.4 g force due to gravity in this direction. There are tensions in the string. Now let's have a look at that. We've got a tension at both ends of this part of the string, and tension at both parts, at the ends of both ends of this part of the string. And for the moment, I'm going to call them T1, T2, T3, and T4. And when these particles, I'm using the word particles, when the stone and the ball are starting to move, then the stone will move with an acceleration in that direction. I'm going to call that A1, and the ball will move in that direction with an acceleration which I'll call A2. Now, if we look at the assumptions that we can make when we're actually doing our modeling, we can simplify the situation by doing the following. We firstly assume that the string is light, and that means that the tensions on the right hand side, T1 and T2, are the same as each other. If the string wasn't light, then T2 would be a little bit bigger than T1. Also, T3 and T4 will be the same if the string is light. And of course, we don't need to include the mass of the string in our calculations. So that's a nice simplifying assumption. If we also assume that the string is inextensible, that it can't stretch, then that means that the value of the two accelerations, A1 and A2, must be the same. So as soon as S moves, B moves by the same amount. So the accelerations of B and S are the same. We also assume that the pulley is light, so we don't have to model any effects of the pulley having its own mass, which is a nice simplification. And that it's smooth. So that means that the tensions on one side of the pulley are the same as the tensions on the other side of the pulley. All the tensions are equal. A nice simplifying assumption, another one, is air resistance, that there's no air resistance, so we don't have to include the effects of air resistance, which is good. And also that B and S are point masses. So this means that we don't have to take into account any rotational effects or indeed the size of S when it hits the ground. Are we there yet? Has anyone thought of any more modelling assumptions that we would need to make? Well, I can think of two more. The first one is that G is 9.8 meters per second. And finally, that the system is released from rest. How many of those did you get? They're not always brought out explicitly like that, but we've got quite a lot of assumptions that we make that simplify our model. So on the next slide, we see the diagram again, but we can dramatically simplify things. So with those simplifying assumptions, we can now draw a slightly less complex diagram. 0.6 is it? And 1.4 G. And we've got our two all of our tensions now are the same, so I'm just going to call them just T. The acceleration now there in that direction and that direction are both got the same value. So looking at S, I can write down the equation of motion for S now. F equals ma. F equals ma. And F, what does F stand for? Quite often people say force, and I say, well, what force? We've got lots of forces. And the answer is the resultant force. And we're looking at S as it goes downwards. So the resultant force in that direction is 1.4 G minus T, and that equals the mass of S, which is 1.4, times the acceleration. Then we look at B, and B is going up. And we're looking at F equals ma for B this time. Well, if we look at B going up, then we've got T minus 0.6 G, which equals B's mass of 0.6 times A. So I've got two simultaneous equations here, and the simplest way to solve these is simply to add them together. And when I do that, the T's cancel each other out. So I'm left with 0.8 G equals 2A. And I calculate A is 3.92 meters per second. So that enables us now to answer the question. The question, if you remember, was how long does it take for S to reach the ground? We're told that it's 0.8 meters above the ground when the objects are released, when the system is released from rest. So we've got constant acceleration, so it's our old friend SUVAT, S-U-V-A-T. The displacement is 0.8. We're assuming that because the question doesn't actually say that it's released from rest, but we're making that assumption. We're not interested in V at the moment. We've just worked out that A is 3.92, and we're trying to find T. So the formula that I'm going to use is the one that doesn't have V in it, and that is S equals UT plus a half AT squared. S 0.8, U times T is 0, half, A is 3.92 times T squared, from which we should be able to calculate T is 0.64 seconds, and I've just used two significant figures there. Okay, so how did you get on with that? Did you get all of the simplifying assumptions? Did you get the same answer? Did you use the same method? Anyway, if you did, well done. And that's all for today.